Hey everyone, in this video we're going to talk about section 1.2a and finish up our notes. So our next section is going to be about symmetry. I already have all these definitions written out because this is just a review of what you learned last year in Algebra 2. So an even function is a function that has symmetry with respect to the y-axis. I always like to think of the parent function for y equals x squared, okay? This parabola has that symmetry. Algebraically, we can determine if it's an even function by plugging in a negative x, simplifying algebraically as much as we possibly can, and if we get the original function back, it's an even function. Okay, what this is telling me is that if I take a look at a point, and then I take a look at a point with just a negative x value, so just that symmetry over that y-axis, it still is going to give me out the same function value. An odd function has symmetry with respect to the origin. Okay, I like to think of the parent function for the cubic function. Algebraically, we can determine that by plugging in the negative x, and if we get an opposite version of the original function, okay, meaning that all of those signs on that function are changed. So what that tells me is if I take a point, okay, and then I look at the negative x value version of that point, it will also have the negative y value version of that point. Okay, and then we say a function is neither odd nor even if it doesn't match either description. Okay, that means that it doesn't have that symmetry of either over the y-axis or the origin. And algebraically, if we plug in a negative x, it might change some signs, but we either don't get out the original function or the opposite of the function. So we're going to take a look at some examples. Okay, the first one we have is j of x, and that's equal to x minus 3 squared. Okay, now I want you to picture what that looks like in your mind, and just picturing what that looks like in our mind, we should be able to tell if this is going to be odd or even. Okay, however, we're going to do this algebraically and get some practice with that. So to do that, we are going to take our function, and I'm going to plug in negative x values. So what that means is that everywhere I see an x, I'm going to plug in a negative x. Now we need to simplify this out a little bit. And in this first example, we're going to have to do a little bit of algebra to get us there. Okay, so one thing that I'm going to do here is I'm actually going to factor a negative out of both of these. I'm going to try to see if I can either get the original function back or if I can make all the signs be opposite. So factoring out a negative, that's going to leave me with a positive x, and it's going to leave me with a positive 3. Okay, now pulling out that negative, I'm still squaring that. So all of this is still happening inside the parentheses. So next I'm going to use my properties of exponents, and I'm actually going to pull a negative 1 out of the parentheses. Okay, but because I pulled it out of this parentheses, that exponent still applies, so I'm still going to have this being squared. Okay, and then simplifying from here, okay, well, what happens when I square a negative 1? That ends up giving me a positive 1. Okay, so I'm left with x plus 3 squared. So let's look and see what happened. Okay, we started off with an x minus 3 squared, and when we simplified, we ended up with an x plus 3 squared. That doesn't look like the same, okay, so it's not even, and it's not odd because not all of my signs have changed. So in this case, this is neither. Okay, now the way that I'm going to expect us to justify it can't just show me this and say neither. Okay, we're going to have to say because j of negative x does not equal j of x, and j of negative x does not equal negative j of x. Okay, so I want you to write out exactly what I have written here. That's going to be how you justify that. Okay, next one we're going to look at is h of x. Okay, h of x is equal to 2x to the 4th minus x squared plus 5. So again, we're going to plug in a negative into all of my x's. So I'm going to have 2 times negative x to the 4th minus negative x squared plus 5. Okay, so going from here, I know that if I have a negative to any even power, that's just going to end up undoing all of those negatives because this is negative x times negative x times negative x times negative x. Since there's an even number of them, it will end up being positive. So I have positive 2x to the 4th. Okay, now here, this portion ends up being a positive x squared, but I still have that negative there, okay, and that didn't get affected by any of those negatives, so I still have a minus x squared, and then my plus 5 never had a negative x, it was always unaffected, so that is a plus 5. So we started off with positive 2x to the 4th minus x squared plus 5, and we ended up with positive x to the 4th minus x squared plus 5. So we started and ended with the same function, so this is an even function. say even because h of negative x equals h of x. Okay, last one, k of x is equal to x cubed plus 3x minus 1. So k of negative x equals negative x cubed plus 3 times negative x minus 1. Now, remember, when we have a negative x number, etc., raised to an odd exponent, that means it's going to end up being a negative, because what we have here is we have negative x times negative x times negative x 3 times. 2 of those will be positive, but we'll still be left with 1 negative. So we have negative x cubed, and see here, now I can drop that parenthesis because I know that I'm going to end up with 1 more negative. Okay, so I have negative x cubed, then 3 times negative x is negative 3x, and then I have my negative 1 that never had an x, so it was unaffected. So we started off with positive x cubed plus 3x minus 1. We ended up with negative 3x minus 1. Did I say plus 1? I can't remember. I mean minus 1. Regardless, okay, I don't start and end with the same thing, okay, so it's not even. And 2 of my 3 signs changed, but that third one still was negative. So again, this is going to be neither. And yes, we got to write it out. Because k of negative x does not equal k of x. And k of negative x does not equal negative k of x. So close, but not quite. Okay, our last 2 examples on this page are just going to be looking at some graphs. So again, we are trying to determine the symmetry that we have. The best way that I like to do it is I like to look at a couple of points and just kind of map out what happens to my points. So for instance, let's see, I got this point and I got this point. Okay, and I know that it's not exactly at 1, we'll call it 1.2. Okay, so this point here, I have 1.2, negative 3. And then over here, looks like I have negative 1.2, comma, positive 3, okay? So I have the same point, except all of my signs are opposite, so this is going to be an odd function, okay? It has that origin symmetry. For g of x, okay, it's a parabola, and we want to be really careful because I know that the inside of us wants to say, it's even. Is it though? Okay, because let's look at some points. Okay, so I have a point here. I have 3, 1. But does negative 3, 1 exist? Okay, negative 3, 1 would be over here. Unfortunately, it does not. Okay, it looks like that point, that mirrored point on the other side with symmetry is negative 1, 1. Okay, so because I don't have that symmetry over the y-axis, even though it does have symmetry over x equals 1, it still doesn't count. Okay, so this is neither. All right, ready, go ahead and flip over your page. We have one last topic we are going to discuss. Okay, and this topic is actually super duper important, and I'm glad that we're talking about it now. It's end behavior, okay? Now, when we talk about end behavior, we want to know what happens with what the function does as the inputs get massively large, okay, as it goes to infinity, or as it gets really, really small, okay, really big, small numbers, so going to negative infinity. End behavior is going to be more of a formal way of discussing like horizontal asymptotes when we get to discussing functions that have those. And it's more specific, okay, we're going to state what the graph does on each side of the function as long as the domain exists going to either side. Now, in pre-calculus and later calculus, okay, that's the whole purpose of why you're here, we're going to write the end behavior in what we call limit notation, okay? So, for example, this is what our limit notation is going to be. Let's talk a little bit about what that looks like. Okay, so first I'm going to just start off by drawing, let's draw ourselves a little graph, okay? And we're going to have a function, maybe our function looks like this, okay? So what this is saying, and how we say this out loud, is the limit of f of x as x goes to infinity is L. Let me write that out. So on our graph, I can see that my function here looks like it's approaching some sort of horizontal asymptote. Okay, the y value that it's approaching, like on my y-axis, would be y equals L. Okay, so what this is saying is that long term, as my values go to infinity, okay, as my x values keep getting bigger and bigger, my y values are all approaching this value. Now, okay, it might cross the horizontal asymptote and then maybe dip back down, but it's staying around what this y value is. Now, in Algebra 2, if I recall, and I haven't taught Algebra 2 before, you wrote your end behavior like this. As x approaches infinity, f of x approaches L. Okay, these two things are saying the exact same thing, just this version here is what we're going to use in pre-calculus because that's what our calculus notation is going to be. Might as well learn it now because we're going to need to learn it again in the spring. Okay? So similarly, what this looks like is this is just talking about what the other half of the graph does, okay? The limit as x approaches negative infinity of f of x is equal to L. So in this case, our graph might look like this. Okay, it's just saying that as I'm going backwards, so if I'm going to the left on my x-axis, my negative x values this time are approaching approaching whatever y equals L is, whatever that value is. So in Algebra 2, you wrote as x approaches negative infinity, f of x approaches L. Okay, again, this is going to be our new way of saying that. So in example 4, we're just going to practice finding the end behavior of these functions, okay? And right now we're going to just mainly be focused on looking at the graphs and doing so. Eventually what's going to happen as we go into the spring, okay, as we hit our 7th unit or our first calculus unit, we're going to learn some maneuvers of how to do it just from the function. Okay, but right now we're not there. It's August. We're looking at the graph. Okay, so our first function that we have is f of x is equal to the natural log of x minus 2 plus 5. Okay, you may or may not have learned about the logarithm functions. Doesn't even matter. Again, we're just looking at that graph. So we're going to do the left and right end behavior and writing our answers in limit notation. So I'm just going to set up what we have. So the limit as x approaches infinity of f of x equals, and the limit as x approaches negative infinity of f of x equals. Okay, so let's go to, let's look at the first one. We're going to positive infinity, okay? What's happening? Well, maybe this isn't the best example to start off with because you might be thinking, aha, well, it looks a lot like this, Mrs. Brown. You're right. But it's not really clear as to like what it's going towards. Like I'm not seeing a super clear asymptote. Okay, and that's actually because a natural log function or any sort of logarithmic function actually doesn't have a horizontal asymptote. It just grows super slow. Okay, so we're going to say the limit as x approaches infinity of f of x is equal to infinity. Okay, it's just going to keep getting bigger and bigger and bigger and bigger forever. It doesn't have an asymptote it goes to. Okay, so then on the other side, the limit as x approaches negative infinity of f of x equals, well, what happens to our function? It doesn't actually go to negative infinity. It kind of looks like it hits a vertical asymptote here, okay? And it does. My graph is not defined past, looks like x equals, what is that? 1, x equals 2. Okay, so because I'm not even defined on this part of the graph, I'm going to say that this limit does not exist, or DNE. Okay, so in this case, it doesn't go there, so we don't have a limit. Let's look at our next example. Maybe that's a more friendly one. Okay, this time we have an exponential. We have g of x is equal to 2 to the x plus 5. So let's set up our limit notation. All right, so let's look at what happens as we move to the right. Well, what do my y values do? Well, this is an exponential. They keep going up, so I'm going to say that we go to infinity. Okay, now on the other side, as we go to negative infinity, what's happening to this? Well, if you remember anything about exponentials on from Algebra 2, you'll know that there is a horizontal asymptote, and here we can see that that horizontal asymptote, that vertical shift, is going to be 5. So that limit is equal to 5. Okay, next up we got a rational function. This is k of x. It's 2x plus 5 over x squared minus 2x minus 3. All right, so let's go ahead and set up our limit notation. All right, accidentally got cut off. Anyways, we have our limit notation. Let's see what happens. So our rational function has some stuff going on in the middle, but again, the cool thing about end behavior is, guess what? We only have to look at the ends. Okay, so as we go to positive infinity, what's happening to my function? Well, if you remember anything about rational functions from Algebra 2, you know that we have some horizontal asymptotes. Most of the time they're the same, but later on in this semester we're going to learn that they don't always do the same thing. Anyways, it looks like this one is just approaching 0. Okay, on the other side, looks like our rational functions doing the same thing, so they're both going to 0. All right, we got one more. We have another rational function. This is m of x. It's just in factored form. Looking here, looks like, again, we have some stuff going on in the middle, but we're just interested in the two ends. So the limit as x approaches infinity of m of x is equal to, looks like we are approaching 2. And the limit as x approaches negative infinity of m of x is also approaching 2. All right. That's all we have for this video. What we've learned within this section is going to help us describe all sorts of functions, which is going to be a main focus for the pre-calculus portion of this class. That's all I have in this video. I will see you all later.